Hello everyone, thank you for coming to this conference. And my name is Marcos. I am a doctor in geochemistry and geochronology, where I recently finished my PhD at the University of Queensland. My research today is titled Holocene Microbialite Geochemistry Records Secular Influence of Terrigenous Flux on Water Quality for the offshore southern Great Barrier Reef. And thank you to all the people that have been involved or have collaborated or given me inspiration and ideas and the improvement of the technique that we have developed. And this is one of part of the presentation, how we develop this technique to analyze and microbialites, trace elements in microbialites, but put them in a context of history. And so I can show you here the people that has been involved, my supervisor, Gregory, Jian-xin, and my colleagues and classmates, and also the people that helped me to collect the course. Those brilliant scientists has been an inspiration. So this study area is Heron Island and One Tree Reef. Who wouldn't want to visit those idyllic paradise? And I was lucky enough to go there and collect some samples. And this is the study area, the Capricorn Bunker Reef group, which is the southernmost part of the Great Barrier Reef. And you can see also in picture B and C where the cores were collected. And this is the way how they were collected in a platform that was placed over the reef. And the platform, of course, I'm not showing here, but it could be moved through one location, from one location to another, using a barge. So we put this platform in the barge and we could move it in high tides. And you can see also in the picture how those beautiful cores that were collected. So from the core recovery, we obtained 17 cores collected. We have done more than 200 dates for those cores. We collected samples from a depth of 30 meters. And so we have a very abundant paleoclimate record that what we can use, and especially for the water quality, which is the center of this presentation. And so in this study, we use 97 samples for trace element, and from those 80 were microbialite, which is the main part here. And the main proxies that we used were total rare earth elements in the samples, also the ratio of yttrium holmium, and neodymium ytterbium. Let me give you a context of the microbialites. The microbialites grow over the coral, and when they grow over the coral, we have two factors here. Is the thickness, and we know that the thickness of the microbialite is dependent of the rate growth. And from previous literature, we know that they grow at a rate of 2.9 millimeters per 100 years. And there is a lag time where the microbialite doesn't grow, or it has to settle in the substrate, which is approximately 150 years. And now we have also the age of the substrate, in this case coral. And so we came up with this idea of constraining the age of microbialite based on that data, although it's a much more higher range of margin error, but we could locate, or we could put this data of trace element in an historical context, which is pretty amazing. And so another finding that we have was that in the Paleosol there were growing framboidal pyrite, and that is an indication of anoxic environment, indication of turbid environment, and high in nutrients. So let's see the rare earth element behave in marine environment in a very characteristic way, and this illustration shows the main characteristic of rare earth element and yttrium in seawater. The interesting is that microbialites preserve that signature in their carbonate, in their precipitation, which is the main part here. Well, to understand better this pattern, we have a light depletion of the light rare earth element depletion, and high yttrium, and also there are some anomalies that are present in this pattern, which is negative Syrian anomaly, positive Lantayan anomaly, and two minor positive anomalies, which is gadolinium positive anomaly and lutetium. And that is how we came up with this nice graph here, which show us the characteristic of these different patterns in the different type of samples. So Paleosol is more similar to terrestrial input, so it's almost flat, because it indicates that have high content of all the rare earth elements. And then we have the other different patterns, especially the microbialites, and we can compare that with previous data. And so putting that in historic context, we can take, for example, yttrium holmium and all the samples that we took from microbialites, and we can see that it shows a pattern where you can see the arrow, the red arrow, showing a pattern of a high and low values of yttrium holmium, which indicate high values indicate clean water and low values indicate turbid water. And the interesting is that these patterns correlate very well with another environmental factors, such as the monsoon, ENSO, or sea level fall. And so as a sum up, we can conclude that microbialite geochemistry was successful capture microbialite geochemistry successfully captured broad water quality conditions through much of the ensuing Holocene. That recovered Paleosol provide direct samples of a local terrigenous sediment, and also the interesting is that those interval high and low water quality correlate very well with global climate records. and fluctuations, especially in sea level. So thank you very much.